Question 14a, Part 1. Show that for k greater than 0, 1 over k plus 1 squared minus 1 over k plus 1 over k plus 1 is less than 0. The strategy is to add these three fractions together by finding a common denominator. So we have 1 over k plus 1 squared minus 1 over k plus 1 over k plus 1. So to find the common denominator, we multiply the first fraction by k over k, the second fraction by k plus 1 squared over k plus 1 squared, and the third fraction by k outside of k plus 1 over k outside of k plus 1. Multiplying all that through, we have a common denominator of k outside of k plus 1 squared among all three fractions, and the numerator of the first fraction is k, the numerator of the second fraction is k plus 1 squared, and the numerator of the third fraction is k squared plus k. Now we can add all three numerators together. And that equals k squared plus 2k minus the expansion of this perfect square, k plus 1 all squared, so minus k squared plus 2k plus 1 over the common denominator of k outside of k plus 1 squared. And that equals k squared plus 2k minus k squared minus 2k minus 1. And the k squared cancels with negative k squared here. And 2k cancels with negative 2k there. And that leaves negative 1 in the numerator. So that equals negative 1 over k outside of k plus 1 squared. Now this is less than 0 since k is greater than 0. Hence the denominator, k outside of k plus 1 squared, is greater than 0. And we're dividing a negative numerator by a positive denominator. Part 2. Use mathematical induction to prove that for all integers n greater than or equal to 2, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus ... plus 1 over n squared is less than 2 minus 1 over n. The first step is to show the statement is true for some value of n. And in this case, the smallest value of n that we can test is n equals 2. Now the left-hand side of the statement is equal to 1 over 1 squared plus 1 over 2 squared, which equals 5 over 4. And the right-hand side of the statement equals 2 minus 1 over 2, which equals 3 over 2. Now the left-hand side is less than the right-hand side, hence the statement is true for n equals 2. Next, we assume the statement is true for n equals k. That is, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus ... plus 1 over k squared is less than 2 minus 1 over k. Next, we show the statement is true for n equals k plus 1. That is, we need to show that 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus ... plus 1 over k squared plus 1 over k plus 1 squared is less than 2 minus 1 over k plus 1. Now from part 1, 1 over k plus 1 squared is less than 1 over k minus 1 over k plus 1. So if we go back to part 1, we just rearrange this inequality and make 1 over k plus 1 squared the subject. Now from the assumption, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus ... plus 1 over k squared plus 1 over k plus 1 squared is less than 2 minus 1 over k. So that's this part of the left-hand side of the assumption is less than this. So that's from the assumption itself. But from part 1, 1 over k plus 1 squared is less than 1 over k minus 1 over k plus 1. So combining all that together, we can see that the negative 1 over k plus 1 over k cancel. Hence, this side here, the left-hand side, is less than 2 minus 1 over k plus 1. Hence, the left-hand side is less than the right-hand side for n equals k plus 1. Therefore, by the principle of mathematical induction, the statement is true for all integers n greater than or equal to 2.